Hello?
Sure.
Yeah.
Yes, you can start to sound. I can hear you.
Can you see the slide?
Yes.
Okay. So, hello everyone. This is a new year and I am very pleasure to be the first person to start the seminar this year. So, it's gonna a series about deep learning and hopefully we will have a lot of information during the series. And today's presentation, I would like to present about self-supervised representation learning. Self-supervised representation learning is a very essential field in every machine learning algorithms. And in this presentation, I would like to provide you guys about basic foundation of self-supervised learning and also representative methods and also some of the interesting approaches using in the field. So let's start the presentation. So what is the representation learning? So representation learning is basically learning a feature vector that best describe our input, maybe an image. Given an image using a neural network, we can extract the essential information containing in the feature vector. Maybe the color, maybe the height, weight, etc. And the aim of the representation learning is somehow learn a low dimensional latent space representation of a vector so that the latent space can be well organized or satisfy some good properties so that we can easily perform downstream tasks on the latent space. For example, here we have the default representation which is very messy, and we can somehow use a neural network to grouping them into similar representation vector so that it can be separable. And if we apply the classification algorithm on this good semantic representation space, we can easily classify them into different groups. And how can we learn the representation in the setting of self-supervised learning? Self-supervised learning means that we don't have label for the data. We have a bunch of images, and we use the images as the input, and we try to learn the representation. This is modeled by the deep neural network to output a representation vector. But usually in the setting of self-supervised learning, we have to have label for the, for example, here the latent vector, latent or the representation vector. But in the setting of self-supervised learning, we don't have label, right? So how can we let the neural network learn the representation automatically without the need of label? So it turned out that we can injecting biases about how we think that a good representation is, and then we can design a retest task so that the neural network can solve it, where the task need to be designed so that it requires to understand about the image. If the neural network understand about the semantic or about what is the image is, it can solve the task. If not, it cannot solve the task. So there are many inductive biases here, and I will introduce along the presentation. So let's move on to the first paper, which is our work in this field, recent work in this field. We published it in IEEE Access, and it's called Dimensional Contrastive Learning for improving self-supervised learning. So, but first we start with some state-of-the-art method in the field. So current state-the-art of methods in the field can be classified into two main approaches. The first approach is use contrastive learning, and the second approach is use non-contrastive learning. So in contrastive learning, the main inductive biases are they said that the input representation should be distinctive among instances, and it should be invariant to augmentation. For example, if we get an input image and we try to augment it, it still contains the same information, and the feature representation is nothing but the information about the input image. And it means that if we extract the representation, the feature representation of the augmentations of the input image, the feature representation should be unchanged or invariant to augmentation. In that sense, they design the framework so that is invariant to augmentation, and it gives the representation of every image in our dataset distinctive. How to do that? The first paper in this line of work is MoCo. MoCo represents a general framework where given an input image, we can use some random data augmentations to project it into two images, the first augmentation and the second augmentation. And furthermore, we will use a deep learning network to embed it into the latent space, which produce the Q here. Q here is nothing but a representation vector, and they name it curry. And the same network will be used to embed the second augmentation to be a key. And the Q and key here should be invariant to augmentation, right? So we have to make the Q and key to be similar. And to make every input representation should be distinctive, they further introduce the negative samples. The negative samples are nothing but the representation of all the image rather than the considered image. So in the bad side we have n images. We consider the first image and the second to the n images are negative samples, and the representation of the negative sample are negative keys. And constructive learning try to make the query equal to the positive key and different with all the negative keys. So in this MoCo paper, they further introduce a technique which is called memory queue, so that we can store all the negative key in the queue, and then we can easily, because they find out that contrastive learning work well where we has a loss of negative keys. So they introduce a queue so that we store the keys inside a memory queue for negative keys. And we also find out that if the encoder and the momentum encoder here is the same, it will make instability in training. So they introduce a technique called memory update, so that the momentum encoder is just a momentum copy of the encoder here. So later work simply find out that if we just embed image into the latent vector and try to apply directly contrastive learning loss. This is not very effective because this encoder, the representation vector here is using for downstream tasks, and it may be differ from different downstream tasks. So forcing it to be the same among different downstream tasks is not an effective way. So because we more simply introduce another technique called projection. So they consider that this representation vector is very general information about the image. And if we consider a specific pretest task, then we have to project it into a smaller space or a specific space for that specific task. So they introduce another projection layer, projection head here, so that the representation vector can be projected further into the specific task representation vector, which is called embedding space. And they apply the contrastive learning on the embedding space, and it is more effective to learn the representation vector here, which will be used in the downstream task. That is the line of contrastive learning. And recent studies in self-supervised learning turn out that we can reduce the inductive bias, which is the input representation should be distinctive among images in the dataset, and should keep the inductive bias, which is invariant to augmentation, is enough for get good representation vector. So they however, they should somehow reduce the inductive bias invariant to augmentation a little bit. Before it's very strong that it should be invariant to augmentation, but now they reduce to the representation of each augmentation should be predictable to other augmentation. Predictable, not the same, but predictable. It means that if we apply a predictor to one augmentation vector, to one embedding vector, we can predict about another augmentation vector or another embedding vector of another augmentation. So we all introduce the framework which further include a projection layer after the embedding after the projection layer, so that we can predict the embedding vector of another augmentation from one augmentation, from one embedding of one augmentation. And it turned out that if we apply this framework, we can get state-of-the-art performance while we doesn't face the problem, which is collapse usually happen in the contrastive learning. And our work, which is SimCM, also consider representative methods of non-contrastive learning. They analyze that the benefits of the preventing collapse and it's not come from momentum encoder, it's not come from prediction layer, but it's come from the stop gradient here, and they remove the exponential moving average scheme, copy encoder scheme here, and they just use the stop gradient, and they can still learn a reasonable result from this framework. But anyway, the CPM has low performance, so we will consider BO. BO here is the state-of-the-art method. So in this paper, we try, our motivation is somehow try, because contrastive learning has a very long history, so it potentially has a lot of good methods, and non-contrastive learning is relatively new compared to contrastive learning. So is there a way that we can utilize in contrastive learning to further improve the non-contrastive learning? We found that there is a way that we can use contrastive learning to improve non-contrastive learning. We introduced a new bias, which say that representation should be diversity by itself. We call it feature diversity. So that given limited space, let's see it, embedding space, we have limited space defined by the feature dimension D. A vector just has to contain D information, and in order to because we don't have any we can assume that given an input image, how can we extract a lot of information into that limited space, embedding space or representation vector? One idea is that we can somehow making that every piece of information contained in the representation vector should be different from each other or linearly independent with each other, so that our feature vector will become full of information about the input image. So we can apply it. How can we apply it? How can we do that? We can do that by making this is the, let's go to the next slide. So given a batch of images, we firstly encode it into the representation vector, and then follow the standard procedure. We embed it into the embedded space. In this embedded space, we will have n by d tensor. N by d tensor. This is the path direction, and this is the dimensional direction. So our purpose is to making this column vector to be independent with other column vector. So it means that the same index of column vector should be similar, and the different index vectors should be orthogonal to each other. And similar with contrastive learning, which try to making similar among the same instances, representation vector and different with the different among representation vector if they are come from different instances. We apply it along. We apply the contrastive learning along the dimensional direction instead of the batch direction in contrastive learning. And the corresponding loss is shown on the bottom of the slides. It's very simple. We just use the same form of the contrastive learning here, but we apply it along the dimensional direction. And then we use it as a regulator for regular baseline methods. Here we denote it the loss of the baseline, and we incorporate it into the loss by factor lambda. We call it balance weight lambda. So let I introduce a little bit about contrastive learning. So for people who don't know about contrastive learning, as I said before, contrastive learning means that they try to make the representation vector of augmentation came from the same image to be similar, and make it different if the representation vector came from different images. Here, the Q is the curry, the K plus is the positive, is the representation of another augmentation of the same image. And K minus here is a set of all other representation vector which is different from our considered image. And we apply this formulation so we can easily achieve our goal. So this is a more elaborate on the dimensional contrastive loss, but I will keep it. If you have any curiosity, you can find me and I will explain it. Basically, let's say that apply the contrastive dimensional contrastive learning loss, we can have the hardness aware property where we consider the we will pay attention on the different pair of images instead of consider them equally. So, and the pseudo algorithm, and I want to introduce you about the experiments that we usually have to do in representation learning. So in representation learning, we have to do a lot of experiments, and these are some common experiments that we have to do in order to get a paper published. First, we have to compare our methods in a lot of data sets. Representation learning is a very general technique, so it have to be generalized amongst various data sets. Here we have small data sets, Cipher 10, Cipher 100, STL 10, and Eminet 100, which is a smaller version of Eminet. We have to show that our method outperforms previous methods. Some representative methods, some baselines that we have to consider is Mauko version 2, SimClear, BO, and SimCian, which is the basic thing that we have to outperform. And some reviewers require us to perform a lot of matrix comparison. So some matrix that we should consider is top 5 accuracy beside the top 1 accuracy, which we usually use in classification. And if we have some specific matrix, we have to introduce that. Here we introduce the feature diversity, and our motivation is to improve the feature diversity. So we have to show that if apply our method, we need to be improved in the feature diversity. Another matrix is the accuracy on the KNN, which is very popular in the classification. So beside the small data set, we have to make sure that our method perform better on the large scale data set, which is usually embed 1000. And usually it requires a lot of time for us to train our method on embed. It takes around 3 to 7 days to train like 100 epochs on embed. And but the reasonable epoch that reviewer usually require 200 epoch or more 1000 epochs. So we should we should make sure that we have enough time to produce the result. Otherwise, they just constantly ask us about the result. And another experiment that we should perform is transfer learning. Transfer learning, which means that when we achieve the representation vector, we should somehow apply it to downstream tasks, because we claim that representation vector should be benefit many downstream tasks. So we should somehow show. Can you open the Zoom again?
I can see it.
Oh, you can see it. Okay. So
Good.
okay. So we have to perform transfer learning on at least object detection. Usually we perform on classification, but we should further perform on object detection at least. And the reason the data set which is small and reasonable for us to perform is Coco data set, not Coco data set. And usually in the paper we should perform a lesson study about the hyperparameters. So in this paper we introduce the lambda weight balance weight, and we show that what is the optimal balance weight for our methods. Here the lambda should be around 0.1, and for the contrastive temperature we also need to perform the analysis for that. So it turned out that the contrastive temperature should be equal to 0.1 also. So in this methods, in our methods, we find out that if you use the 0.1 for the weight and 0.1 for the temperature, we get very stable result. So our method is not very sensitive to the hyperparameter. And furthermore, if we have some space, for example, here in our methods, we try to extract a lot of information, into a small feature vector space, and we all consider that is a good feature of our methods. So we have to perform a specific analysis regarding the dimension of the feature vector. The dimension of the feature vector. Oh, this is not it. Anyway, yeah, we have to perform specific analysis about our special feature of our method. Yeah, and revert very much into some qualitative result. So we can project it. We can visualize our representation space using some technique like TSNE to show the reviewer. Furthermore, one trick here is that usually the representation space is not very informative. This is not very distinctive. So we can use some kind of we can use interclass or intra-class matrix, intra-class distance or interclass distance here to quantitatively represent our feature space. So that is more convincing to reviewer. Yeah, and more if we have more discussion on our method, we can provide more. Anyway, that's my paper. And for continue my presentation, I will provide you guys about interesting direction in the representation vector, representation learning, and also I show some specific domain methods which utilize self-supervised learning, representation learning. So here I present 6 more paper. The first 3 paper is some interesting direction that we can research in the field. The 4th and the 5th paper is representation learning in the field of reinforcement learning, and the 6th paper is the self-supervised learning of speech representation learning. So it applies in the speech recognition in the speech machine learning for speech. So let's start with the first paper, which is mean shift for self-supervised learning.
Wait, Thanh. The Zoom's gonna shut down in like 4 minutes, so let's just have like a 3-minute break and we'll restart the thing.
Oh, that's right.
Okay, okay, let's, so how long is this presentation?
Yeah, it's supposed to be end before 4 o'clock.
Oh, so this is very long, 1.5, almost 2 hours.
Yeah. So how long do you expect for one seminar?
Maybe definitely less than an hour.
Okay. So
You need to finish before 16:30.
for this seminar, I will try to finish it in 30 minutes more, and for next seminars, we will make it short, like in 1 hour. Is that okay?
So, okay, so can we just let's stop right here for today, because we have there are some people who are writing papers and rebuttals. I just want to okay, so there are 3 things that people have to realize, so what is self-supervised learning? Can you say it in a very compact way?
Okay,
What is
so
self-supervised?
what is self-supervised learning? Self-supervised learning means that we don't need label for learning a thing. Self-supervised learning try to ingest inductive bias to learn the information from data without require human label. They usually use pretend tasks in order to inject inductive biases into to guide the model learn the useful information from the data.
Okay, so what is inductive bias then?
Inductive bias is what we think that the data the data is good. For example, here one inductive bias is the representation vector should be invariant to augmentation.
No, that's not inductive bias. What is the definition? So, what you do then is, okay, so there are three things people that needs to understand. Well, what is self-supervised learning? Okay,
Yeah.
and you have shown one example. I think there are many examples for image. Let's say that you have an image and you try to scramble it, and you try to figure out the order of the scramble.
Yeah.
Or if you mask certain P, you try to figure out what that is.
Yeah.
There are many self-supervised techniques out there. I was hoping that you can sort of update this slide so that you have sort of a good number of examples that show what self-supervised learning is. Okay.
Okay. I see.
Yeah. So that would be that would improve your slide a little bit. Okay.
Yeah.
Okay, and also include self-supervised learning is not only
Oh my God.
Recording in progress.
지금 다시 로그인하시면 되고. 지금 몇 개 정도 저희
anh thì bắt tới trong nói như là không đi mượn em cần đi hiện nhiên ông ở bên dưới không ai kêu được nhưng mà cái nói của nó hơi khác của cái nói của thực ra là một cái bài nói cái điểm sân đấu bây giờ sẽ có một cái phong phóng
I'm here.
Okay, I hear you now.
Yeah, can you keep it really short? Sorry about this, but you have a good slide, but I'm hoping that you would not go into too much detail, but essential message.
Oh, yeah. Yeah. That's all.
Okay, I'm hearing you.
Yeah. That's it all for the seminar. So we thank for your comments about the seminar. And next time, I think that the students will also understand about that and making the seminar much better.
Okay, so first of all, I think students should understand the importance of self-supervised. Under self-supervised, you also have contrastive learning.
Yes.
Students should understand what contrastive learning is. Can you explain in a very short way what contrastive learning is?
So, in a short way, contrastive learning is that if the representation vector come from the same image or from augmentation of the same image, so the representation vector should be the same. If it is come from different images in the dataset, then the representation vector should be different. Is that okay for you?
Okay, so contrastive learning is trying to put features that should be close, and features that should be considered far to be far. So if you had like a diagram, you want to have features that should be close to be near each other, and features that come from different source, or that should be different to be far away. That is what contrastive learning is. So contrastive learning involves positive samples, which means that are samples that should be close to something, and negative samples are samples that should be considered far away. So that sort of defines a boundary between positive and negative samples, right?
Yeah.
And contrastive learning does not only pertain to self-supervised learning, but it's a very general method.
Yes.
Right?
Yes.
So, in the context of self-supervised learning, image, let's say, or data, and you augment the data. Now you extract features from the augmented and from unaugmented, or if you have two different versions of augmented samples, they come from the same source, so those representations should be close.
Yes.
And if you had a different source, if you had a different data, then that should be considered a negative sample. And by having positive and negative samples, you are sort of pushing and pulling the representation data.
Yeah, right.
Right.
Yeah.
And if you had and you could do this with label, or you could do it without labels. It's a very general learning method, and here you have used it in the text of self-supervised learning, where you don't have labels.
Yeah.
Right?
Yes.
Students should understand what self-supervised learning is. Self-supervised learning is associated with node label, and is trying to create a task within the data itself.
Yes.
To learn some characteristic of the data.
Yes.
So trying to learn rather than using indefinite, because that's another term that needs to be defined.
Yeah, right.
Self-supervised is trying to learn a characteristic of the data that pertains only to that type of data.
Yes.
And it's, if you have a very good self-supervised learning, and if you have a good representation based on self-supervised learning, you can do very good, you can perform very well on downstream tasks such as classification and regression, segmentation, and so forth. Right?
Yes.
Okay, so today's lecture was about self-supervised contrastive learning, right?
Yes.
And also, I think it's about representation. Okay, representation. So what you want to do? Why do you want to represent the data?
Oh.
What's the key?
Okay. The keys of representation learning is that, so in the world we have a lot of data. First of all, we have a lot of data. We can to utilize the data to learn some information about the data. So without the need of human label, so we use self-supervised learning. We use self-supervised learning. And about the representation learning means that usually the data nowadays is images, which is very high dimensional. And high dimensional.
So that's the key point. Okay, so can you stop just a little bit?
Yeah.
Okay. So representation learning is about representing the data such that the innate, I-N-N-A-T-E, innate characteristic of the data is survived, whereas other parts or other properties of the data which can vary, but which can vary. So for instance, if you're trying to represent a pencil, the pencil can be red, blue, whatever color. It can be long and short.
Yes.
So if you had a good representation, you want to have a representation that just says that it's a long wooden part with the black, I don't know what you call it, the carbon. That's the pencil. And you want to throw away the color, the different design, and so forth. You want to represent the data. You want to only the essential part
Yes.
that represents the data.
Right.
So you're sort of compressing the information that the data has, and only leaving the essential part.
Yes. We just extract you for information and we discard any redundant information in the data. So that can be
Yeah, so
contained
you
in
want
a
to
very
know, I
low
think,
dimensional.
Representation,
Yeah.
representation involves dimension reduction.
Yes.
I think dimension reduction is a very important element,
Yes.
and it should be able to, in many cases, reconstruct the original data.
Yes. We can reconstruct the original data also.
Yeah, but that's not always necessary for all tasks.
Yes.
Okay, so you have presented a nice work that that enforces orthogonality between how would you say it? The
Elements of
elements
yeah.
or a certain dimension. Okay, so
Yeah.
between dimensions you have enforced orthogonality, right?
Yes.
Yes. I don't know whether that is necessary all the time. You've associated that with making the with compactness. Okay.
Compactness. What do you mean by compactness?
So you had a nice picture of a jar with stones, and you wanted to pack in lots of stones with essential information.
Yes.
And in order to do that, you, I think, mentioned that the dimensions have to be orthogonal. So
Yes.
here you had, so the first dimension is orthogonal to the fifth dimension,
Yes.
or the sixth dimension, right?
Yeah. So every dimension should be linearly independent from the others. So that orthogonal or linearly independent. It means that each dimension should be contain different kind of information. If two dimensions contain the same or related information, then we just use one dimension with the same information, and it's not good for our representation vector because we have a fifth dimension to be learned. Fifth dimension D to be learned.
You know what? I would like to, if you want to carry extend this work, okay? I think you should think about the information that is contained in this block. Okay?
Yes.
So you represent two blocks here, right? You have two blocks.
Yes.
For BCL, you have the upper block and the lower block. So also on the right hand side, you have the upper block and the lower block, right?
Yes.
I think if you, rather than try to think about orthogonality, I think what you want is you want to have a block that has the most information.
Oh, correct, correct.
Okay? So, if you have time and you want to work on it, or anybody, think about a method that contains the most information in that block.
Yes.
Okay?
That is a very general approach, I think.
Drive an algorithm that allows you to contain the most information.
Yes.
Okay?
That maximize the information inside this block.
Yes. And information is represented by the entropy.
Yes, maybe entropy, maybe other kind of matrix.
Okay.
Yeah.
Okay. Okay. So that's I think students should understand what self-supervised, contrastive learning, and what representation learning is. For this year, I would like students to think about multimodal representation. So you have image, you have sound, you have text. How do you find a representation, a good representation for all of this?
Oh, I see.
So you're looking at one situation, you're looking at a situation, you take a picture, you also use a microphone, and you also have, let's say, a summary,
Yes.
or whatever was said, whatever was spoken by a person, or maybe some audio information. You want to combine all of this, or these three sensory information, into some compact form that would provide the most information for performing various tasks.
Yes.
So if anybody who wants to work on this should work on multimodal representation.
Oh, I see.
Okay?
Okay.
And they should also have a philosophy of what this representation, the characteristic of the representation.
Yeah.
Okay?
Mm.
Okay, so I'm done here. So thank you for the presentation. I hope you can update it to include many more self-supervised methods.
Yeah.
For one, the jigsaw puzzle, the black and white, and you try to colorize in it. You know, there are many ways of doing self-supervised learning. Okay?
Yeah.
Now, I also would like everybody to understand there is no theory on this, but this is I've heard this thing from many person. The representation, the best type of representation should be able to reconstruct the original data. Okay? So we have so you have slide number 7. Can you go to slide number 7?
Yes.
So this representation, the right-hand block, let's say you have some right-hand block. That right-hand block should be able to, you should be able to create, reconstruct the original image from that small block. Okay?
Yeah.
There are many criteria. You can, but one criterion for that small block is to do good classification. But here, without thinking, you're doing self-supervised learning without thinking about downstream tasks. This representation should perform well for many different kinds of tasks.
Yes.
And because you don't know, you want that block to represent the original image. Okay? And that's what you should be striving for. That's what you should be working for. So that the small block can create the original image, or the original sound, or the original data.
Yes.
Okay? And that's the best kind of representation. That's the best kind of self-supervised learning.
Yeah.
Okay?
Yeah. Right.
Okay, so I stop here. And thank you. And we will continue. We will have our seminar again next week.
I see.
Okay.
See.
Hyunbin, who is presenting next week?
It's not next week, but it's on the 9th of February. It's due to an MT.
Huh?
Due to MT, we are not going to have any presentation.
Next week we're gonna have an empty. So we will not have the seminar, but the following week
Okay.
we will have. Yeah.
Okay.
And Nguyen will inform you the next version of the group, of the seminar group.
Okay. Okay, please update the slides. Okay, thank you very much.
Yeah, I will update slide and send to you.